So today our mathematician spotlight is Colin Adams. He's the Thomas T. Reed Professor of Mathematics at Williams College, and he'll be giving the Ketal lecture tomorrow. So that lecture will be at 4:30. It's a 1 hour or 50-minute lecture. And he'll be talking about his research with undergraduates in knot theory. If you come and you find me and I write down your name, I will give you 10 points on your homework for coming. That's supposed to be an incentive for coming. I believe I've told you about a lot of talks this semester, and I think 0 people have gone to any of them, which is okay because they were job candidates. But Colin Adams is a really good speaker, and so I actually think you should come to this one. So I'm giving you an incentive to try to let you feel that it's probably a good idea. You don't have to come. Okay, so let's see. First of all, he's a Thomas T. Reed Professor of Mathematics. So we've been talking about the levels of academic jobs. So if you're on the tenure track, you come in at assistant professor. 3 years later, you get reappointed. 3 years after that, you might get associate professor with tenure. 6 years after that, you might get full professor. There's pretty much nowhere to go from there unless you get a named chair. So that's what he has, a Thomas T. Reed Professor of Mathematics chair at Williams. So each of those bumps gives you a salary increase and, of course, a prestige increase. So he's at the top. He studies hyperbolic 3 manifolds and knot theory. So we talked about knot theory a little bit the other day when we talked about Autumn Kent's work. But knot theory is you take a string. It should be free at both ends, which this one is not. And then you do something with it. You knot it up in some way. And then at the end, you glue the ends together, which I can't do because I don't have ends. And suppose that I do this, and suppose my friend does it too, like my friend Daniel. Then the question is, are our knots the same or not? And so if they look a little bit different, then maybe I'll just move mine around a little bit. Maybe I'll just move it around to make it sort of look more like Daniel's. I don't know what to do. So it's the big question in knot theory is, can you come with a knot invariant? So that if I have my knot and it looks kind of like this, and he has his knot and it looks kind of like that, and we compare them, we can tell whether they're different without having to move it into lots of different ways. So Colin Adams does research with undergraduates every summer at the small undergraduate research program, which I encourage all of you to do undergraduate research, maybe after your sophomore or junior year of college. And they came up with this new invariant called the petal number. So what that is you take all the sort of loopy bits of the knot, and you push them to the outside, and you push all the crossings to the middle. So I started with a kind of a randomish knot, so I didn't practice this in advance. But let's try pushing all the crossings to the middle. The longer you talk about it. Anyway, so there, look. It looks kind of like a flower, yeah? Look at that great flower. So the petal number is what happens when you push all the crossings to the middle. You see how many petals you get, and that's something that they came up with. So he's going to be talking about that this afternoon. That was something that a bunch of undergraduates came up with to advance human knowledge in the area of knot theory. Pretty neat, huh? Okay. So, good. See you tomorrow at 4:30. Okay, so the last time we talked about changing double integrals into polar coordinates. So changing x, y coordinates into polar coordinates. In particular, to do double integrals. So recall that if you had dA, so you were taking a double integral over some region of some function, dA. Well, in rectangular coordinates, that's dx dy. So we have a double integral, first one with respect to x, second one with respect to y, or vice versa. And when you convert to polar coordinates, well, the coordinates there are r and theta. So we have dr, d theta. But we don't just say dx dy equals dr d theta. We have this integrating factor, r. And that's basically because when things are further out in the r theta plane, r is bigger. So you have to multiply. It's like a stretching factor. That's the idea. So today, we'll talk about changing coordinates to other variables. So if you are integrating a round type function over a round type region, it makes a lot of sense to convert to polar coordinates. And if you're doing something else, like we'll see a sort of a diamond-shaped function over a diamond-shaped region, it makes sense to convert to like diamond-shaped coordinates, whatever that might mean. So that's the idea. You might want to convert to coordinates other than circular polar coordinates. That's the idea of today. But the first thing I want to do is an amazing magic trick. So I think it was just before vacation, we were doing our trick of if you have a double integral that's impossible in one order of integration, you switch it to the other order of integration. And I think it was Parker who said, like, how is this? We just did magic. We switched to order of integration and something magic happened. That was you, right? Yeah. And it's kind of like a magic trick. In that case, it wasn't really a magic trick because our bounds of integration changed in a way that helped us to integrate. But the following thing really is a magic trick. Well, not really. I mean, it's math, but it's a really great idea. So I'll call this Gauss's great idea. And this was really an idea of changing an impossible single integral into a double integral that makes it possible to do. So before we get to Gauss's great idea, I'll do the setup. So you have probably seen this curve, the bell-shaped curve, yeah? The normal distribution. So this is used all the time by our friends in statistics and psychology and economics and really anything that measures things. So 0 is here, and this goes all the way off to infinity in both directions. And this is, it does a pretty good job of measuring things like height of people in a population. So the average height is here, and then a lot of people are around the middle and not so many people at the ends. The equation for this is f of x equals 1 over square root of 2 pi times e to the negative x squared over 2. So today we'll be trying to find the integral of e to the negative x squared dx. Here's why there are these other constants in this equation. So for the bell curve, the first thing that you want is you want the inflection points, so the place where the function goes from concave up to concave down, or concave down to concave up. Those are the two inflection points to be at plus or minus 1. This is something that people want. And so that is why this divided by 2 is there, to make the inflection points come up at plus or minus 1. The other thing that people want is they want the area under this whole thing to be 1. So that if you just take areas of this, it can be the probability of falling in that region. So you want the whole area to be 1, which is what this constant is about. So for the actual bell curve function, we have those two constants in there. But I hope you agree that if you were able to integrate this function without the constants, you could also integrate this function with the constants. So suppose we know, for instance, that our population is shaped basically like this. We know it's a sort of a e to the negative x squared type of thing. We would want to find the area under this thing so that we could divide by the area and then get area 1. Okay, so suppose we want this. We want to find the area under this curve so that we can tell our friends in economics and psychology, oh yeah, this is what, you got to put this factor on the front. So we'd want to find this integral. And usually when you're doing things with the bell curve, you really only care about like between negative 5 and 5, because most people fall within 5 standard deviations of the mean. But actually this goes from negative infinity to infinity. So we want to integrate this function from negative infinity to infinity. Okay, let's do it. So can you please tell me the antiderivative with respect to x of e to the negative x squared? Yeah, can't do it. That's it. So has no antiderivative. So we're stuck. But we need it. We need this. So let's call this A, but we need to find this area. We can't just be stuck. I imagine that people were probably stuck on this for a really long time. It's because the clever trick for doing this is not at all obvious. Okay, so here's the idea. We want this number. It would be just as good if we found the square of this number, because then we could just take the square root of it and we'd get the number. So if a is this integral, then a squared is this integral e to the negative x squared dx squared. Agree? Okay, and if you're worried about negative signs, do not worry because area is positive. Okay, so that's the idea. So let's write this out. So this tells us that a squared is, I'm just going to write this out, the integral from negative infinity to infinity of e to the negative x squared dx times the integral from negative infinity to infinity of e to the negative x squared dx. Okay, so this is some number. We want to know what it is. This is also some number. We want to know what it is. So it does not actually matter that this is e to the negative x squared with respect to x. It could be anything. It could be e to the negative Swarthmore squared with respect to Swarthmore. Or it could be e to the negative y squared with respect to y. It's just a variable. So I'm going to call this variable y. So the first one, we'll leave it as x, e to the negative infinity, e to the negative x squared dx, times the integral from negative infinity to infinity of e to the negative y squared dy. Okay. Now, let's see. With respect to x, y is a constant. So here, I'll write this down and then I'll tell you why we can do it. So this is actually the integral from x equals negative infinity to x equals infinity of the integral from y equals negative infinity to y equals infinity of e to the negative x squared times e to the negative y squared dx, dy, dx. Okay. And the reason for this is as follows. So suppose you're going to actually do this. You take the integral of e to the negative y squared with respect to y, and then you'd multiply it by this constant, because with respect to y, x is a constant. So you do this whole thing with respect to y, and then you'd multiply by, that would be a constant, and then we multiply it by whatever we get when we integrate with respect to x. So it's basically like you can take this as a constant and stick it right in here in the integrand. Okay. So this is actually something that you're welcome to do when you're doing integration. If you have a function, if your functions are each only of one variable, you can split it up into multiple parts. Okay. You see the clever trick coming? So the clever trick is to realize, let's see, this is the integral from x equals negative infinity to infinity, integral from y equals negative infinity to infinity. Okay. E to the negative x squared times e to the negative y squared. Yeah, e to the negative x squared minus y squared. So when you have the same base, e to the something times e to the something, it's just e to the sum of the somethings. Okay, now I'm just going to do this in one step without writing it out again, but this is e to the negative parentheses x squared plus y squared. It's okay, yeah? I factored? Okay, so the first really great idea was to take the square of the thing that we wanted, a squared. And then the second great idea was to put it into two different variables. And now the third great idea is to say, oh, x squared plus y squared. That's r squared. So that's the idea. Idea, convert to polar. Polar coordinates. Okay. So let's do it. So if we convert to polar coordinates, we'll be going from theta equals something to theta equals something. Let's fill that in a minute. From r equals something to r equals something. We'll fill that in. E to the negative x squared plus y squared. In polar? R squared, yeah. X squared plus y squared is r squared. Times, okay, this part, dy dx, that's our dA. So now we have to multiply by dA. dA in polar coordinates? R dr d theta. Yes, R dr d theta. Because we have this extra multiplying factor, because things are bigger when they're further away. I see you smiling. It's going to work, right? Yeah. Before, we couldn't integrate e to the negative x squared with respect to x because there was no 2x on the outside for us. But now, there's an r on the outside, which is essentially the derivative of the inside. So it's going to work. Yes! So now that we know it's going to work, let's fill in these limits of integration. So we were integrating over the xy plane from x equals negative infinity to infinity. So that's the whole x-axis. And from y equals negative infinity to infinity. So that's the whole y-axis. So our region of integration is the entire plane. So let's set that up in terms of polar coordinates. So r we want it to go from the origin all the way out. So r should go from 0 to infinity. And theta, we want it to go from 0 all the way around. So theta should go from 0 to 2 pi. Okay, let's do it. Okay, so if you like, you can put on blinders and just do the r part first. So this is the integral from theta equals 0 to 2 pi of, let's see, the integral of e to the negative r squared times r. It's something like e to the negative r squared. This is my way of reverse engineering a u-substitution. If this was my function, I took its derivative, I'd get e to the negative r squared times negative 2r. But all I have here is an r. So I have to multiply by negative 1/2 to make it work out correctly. So that's the antiderivative of e to the negative r squared times r. And I'm going to substitute in from r equals 0 up to taking the limit as r goes to infinity, d theta. OK, let's do it. So this is the integral from theta equals 0 to 2 pi of, OK, first we plug in the limit as r goes to infinity of this expression. 0, yeah, because you're taking it e to a negative really big number. OK, so that's 0 minus, let's see, negative 1/2 times what we get when we plug in r equals 0, which is 1. So, OK, so let me simplify this. That's the integral from theta equals 0 to 2 pi of negative 1/2. So 1/2 d theta. So that's 1/2 theta from theta equals 0 to theta equals 2 pi. So it's pi. Whoa! Where did pi come from? Once we convert it to polar, of course, it's not surprising that pi might show up, because our theta goes from 0 to 2 pi. But think about back with this bell curve. Did you expect pi to come in? I think it's very unusual, like unexpected, that if you're integrating e to the negative x squared from negative infinity to infinity, pi comes up.
Isn't there something called like Euler's formula or something that like relates pi and 0 and 1?
Oh yeah, Euler's formula relates pi and 0 and 1. Let's put that somewhere. Maybe in a different triumphant color. Sure. Euler's formula. Some people call this the most beautiful expression, the most beautiful equation in mathematics. Anybody remember what it is? You know what I'm talking about? We're talking about? Yeah, e to the I pi plus 1 equals 0. Okay, so that's not relevant for what we're doing today because in particular it has an imaginary number in it. But it relates all the most important numbers in mathematics. 0, 1, pi, e, and the imaginary number I. Yeah, okay, fine. So maybe you were not surprised because e was there. So why wouldn't pi be there? They like to play together maybe. Okay, so we got pi. So there's just one more step. So we got that a squared equals pi, because we started with a squared up here. I guess I should have said this was equal there. Okay, so a squared is pi. So a is the square root of pi. So the area under this function was the square root of pi. Amazing. And if we had decided in advance that we wanted to put our inflection points at negative 1 and 1, we would have had this divided by 2 thing, and so we would have gotten that the area was 2 pi, and that's why this 1 over a square root of 2 pi thing is in the denominator. Yeah. Questions or ideas? Yeah.
I guess I'm just a little confused about how. So we split up the two integrals. When we squared, we assumed that they have to be the same, but somehow we just changed one of the variables, and in order to solve this, I assumed that x and y are not the same. Right?
Oh, I see, yeah. So we were assuming that x and x were the same, and then suddenly x and y are different.
Yeah, because with respect to each other, they're constants.
That's true. With respect to each other,
So
they're
then
constants.
how do we kind of rationalize that logic?
Well, I guess the idea is you could compute each of these separately. Like you could compute one and your friend could compute the other, and they're not really related to each other. Just because they're both x doesn't mean you have to use the same variable for both of them. Yeah. Yeah. It's a clever trick, changing the variable to a different variable and then switching to different coordinates.
I guess like my intuition says it's right, but then there's a part of me that's a little uncomfortable with the fact that we're squaring something, so we're multiplying something by itself. But in order to solve that equation, we have to assume that the two components we're multiplying are not the same.
Yeah, right.
So that for me is just a little bit.
Yeah, right. Maybe it would have been better to call them both x and do negative x squared minus x squared dx dx. But then dx dx, what would it even mean? Right? So it's okay to put them as different variables. It turns out to work out. Yeah. Yeah. Okay. Okay. So these are all manifestations of the same idea of the idea of the change of variables. So let's write out change of variables. So you imagine that you have something in the uv plane, and you can think of u and v as being r and theta. They're whatever variables you're translating into. And then you want, or you have also your same thing in variables x and y. So the idea is that you have some little region over here in the uv plane, which you can think of as the r theta plane. And then you want to transform it with some transformation t into some region in the xy plane. And who knows what t does? It might actually curl it around, stretch it out and curl it around like this. But we want to know. So we have dA, which is dx dy. And you want to transform it into du dv. And you want to know, how is area transformed in my uv coordinates? So you have some transformation of u and v, which gives you x and y. So it gives you x of u and v, y of u and v. And you want to know how it transforms area. And the way that we figure that out is we use the determinant of the derivatives of the T matrix. Because a determinant tells you like an area stretching factor. That's how I think of determinants. If you have the determinant of a matrix that is a box of numbers, it tells you if you take like the unit square, 1 by 1 square, and you transform it under your matrix, what the new area will be. It's just the determinant of the matrix. So it really is, determinant of a matrix is like an area stretching factor thing. So let's define notation. The partial of xy with respect to the partial of uv. This is going to be the determinant of the dt matrix, which is just the box of all the derivatives. So this is the determinant. Let's see, this is an absolute value. Determinant of the matrix, partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. Oops. Okay. So then the big idea, the big formula, is that dA, which was dx dy, is this number, partial of xy over partial uv, this notation, times du dv. So this is exactly the stretching factor that we need as the determinant of this matrix. So for example, so t of r theta is x comma y, which is r cos theta, r sine theta. Then the determinant of the matrix of derivatives, we actually found that before. We found it the last time. So then partial of xy with respect to r theta is r. So this gives us our integrating factor of r. But, yeah, we can also use this for other changes of variables. So this is the integrating factor, that Jacobian determinant factor for polar coordinates, but let's try it for some other coordinates. Okay, so, oh yeah. So before we try it for an example, I just want to tell you that it's not such a new thing to think about. So you know about u-substitutions. Yeah, you did them in calculus when you learned to integrate. And this is essentially a u-substitution, but it's actually a uv-substitution. So this is a uv-substitution. So it goes along with our theme of taking things in single variable calculus and bumping them up by a dimension. So let's apply this method to the one-dimensional case. So suppose you want to compute the integral from 0 to 4 of x times e to the x squared dx. So this is similar to the one that we just did for the bell curve, except that the x is on the outside and the x squared isn't negative. Okay, well, you would decide what your u should be. I think your u should be x squared. So let's say u is x squared, or in other words, square root of u is x. It's easier to write that as u to the 1/2. So let's see. So our Jacobian for multivariables would be like dxy over duv, but here we only have a single variable. So here it's dx over du. So the partial of x with respect to u, x du, is just 1/2 u to the negative 1/2. Or in other words, 1 over 2 times the square root of u. So this is just 1 over 2 times the square root of u. So the way that you would do a u-substitution is exactly this. So you would just figure out your du factor and put it in, and it's exactly the same idea. So in this case, we would rewrite this as, let's see, the integral from u equals something up to u equals something of, let's see, x is square root of u. E to the x squared is e to the u times your Jacobian expansion factor times du. And our Jacobian expansion factor was 1 over 2 times square root of u. Here, we can get rid of the absolute value signs because square root of u is positive. And now the only thing left to do is figure out the limits of integration for u. So if x was 0, square root of 0 is 0. And let's see, if x was 4, let's see, x squared is u, which was 16. And now this square root of u cancels out with this square root of u. And we have our easy to compute thing. So this is just the integral from 0 to 16 of 1/2 e to the u du, which is how you would do a u-substitution in calculus. Yeah.
So how is this different from
So what I just did is u-sub.
So but then why are we bringing in an expansion factor then when we didn't have to do this in more elementary u-sub?
So this expansion factor, like the idea of this little bit is that is what you were doing. You were doing an expansion factor. Because when you say, I'm going to take my variable and I'm going to stretch it, I'm going to square it, you're stretching things. Like if u is x squared, things that are further away have been stretched, like more than things that are close in. So that's why you have to multiply by this like stretching factor. So the idea is that before you may have seen this as purely an algebraic thing, which it is. But once we move it into 2 dimensions, we can see it as an actual geometric stretching thing. Yeah. Yeah. Okay. Okay, so let's try this for a UV substitution. Okay, so suppose that your quest is to compute the double integral over the region R of the function x squared minus y squared dA, where R is the diamond-shaped region whose coordinates are 1, 0, 0, 1, negative 1, 0, and 0, negative 1. I mean, it's bounded by this diamond here. So this is our region R. Okay. Now for this one, you could do this. You're integrating a polynomial. If you wanted to do this, you could decide maybe you want to do vertical slices. So you just go from the bottom, you'd find the equation for this line, you'd find the equation for this line, you'd set it up, you'd do it. Right, you could do it. But we'll try a different method. So let's see. These bounds of integration are a little bit ugly. Let's write the equations of these lines. Let's just write them. Okay, so this line, let's see, it starts at y equals 1, and it has a slope of negative 1. So this line is y equals 1 minus x. Yeah? Starts at 1, slope of negative 1. So another way of writing this line is x plus y equals 1. That's the equation for this line. How about this line? This line starts at negative 1 and has a slope of negative 1. So equation is y equals negative 1 minus x. So you could rewrite that as x plus y equals negative 1. That's the equation for this line. Okay, let's try the other two sides. So if you do this, you can figure out, this is, I think, let's see, this is y equals negative 1 plus x. So this is y minus x equals negative 1, or you could write it as x minus y equals 1. So that's this side. And then for this side, it would be like y equals 1 plus x. So negative 1 equals x minus y. Okay, so those are the equations for the sides. So it would be really easy to write our integration, to write our reason of integration if we used x minus y and x plus y as our variables. That's kind of the idea. You want to find a change of variables that works nicely with your region and with your function. So let's try u being x plus y and v being x minus y. So then our region is u between, let's see, u is x plus y. X plus y goes from negative 1 to 1. And v is x minus y. It also goes from negative 1 to 1. So what we've done here is we've changed variables. We've just taken this and moved it into the UV plane. This was the xy plane, where we now go from negative 1 to 1. Let's see. I'll actually make this with the same scale. This goes from negative 1 to plus 1 and negative 1 to plus 1. So this is the new region that we'll integrate over in the UV plane. Okay. So let's see if we can rewrite our integral. Okay. So we have the double integral over R of x squared minus y squared dA. That's the integral from like v equals negative 1 to v equals 1, of the integral from u equals negative 1 to u equals 1, of our function. Oh, our function. So our function is x squared minus y squared. This has to play nicely with u and v also. You see how it plays nicely? uv, yeah. You can factor this into x plus y times x minus y, which is u times v. Yeah. So it was contrived this way, but who knows? Things happen nicely sometimes. So our function is just u times v. And then we have to multiply by our Jacobian area expansion factor. And then times du dv. So let's figure out our Jacobian expansion factor. So we want to find dxy over duv, which is the absolute value of the determinant of the matrix partial of x with respect to u, partial of x with respect to v, partial of x with respect to, partial of y with respect to u, partial of y with respect to v. Okay, that's what we want. Okay, we want to take the partial of x with respect to u. But that's a bit challenging because we don't have x in terms of u and v. We only have u in terms of x and y, and v in terms of x and y. But it's all right because we can solve for it. So suppose you add these two equations together. Then you would get on the left side u plus v, and on the right side 2x minus 0. Yeah? So you get 2x. So you get then x equals 1/2 times u plus v. And then if you subtract the two equations, we would get 0 equals plus 2y. So we would get y equals 1/2 u minus v. So from these equations, you can solve for x and y. Okay, so now that we have that, so this is the determinant of the matrix partial of x with respect to u. From this is 1/2. Partial of x with respect to v, also 1/2. Partial of y with respect to u, also 1/2. Partial of y with respect to v, negative 1/2. Okay, so now we want to find the determinant of this matrix. So that is 1/2 times negative 1/2, which is negative 1/4, minus another 1/4. So 1/4 minus 1/4 is negative 1/2, and the absolute value of negative 1/2 is 1/2. Okay, so we have found our Jacobian expansion factor. Here it is. And we put it up there. Okay. This 1/2 is not random. Here's why it's 1/2. So the area of this region of integration in the uv plane, see it's from negative 1 to 1. So the width is 2. And then the v is from negative 1 to 1. So the height is 2. So the area of this box is 4. But back over here, the region that we actually want, look at its area. It's also a square. It's a tilted square. It's a square with edge length square root of 2. So the area of this thing is square root of 2 times square root of 2 is 2. So the area of the thing that we're working with is 4. The area of the thing we really want to work with is 2. So we have to multiply by 1/2. So that works out well. That works out everywhere. It's 1/2 because these things were linear. If there were some squares, just like polar coordinates r cos theta, r sine theta, you don't get a constant because it depends on where you are, the expansion factor. But for this one, since it's linear, the expansion factor is 1/2 everywhere. Yeah.
Say for instance, our function integrated was x squared plus y squared.
Yeah.
Are we stuck then, or is there a way to approach that?
If our function was x squared plus y squared, I think we could still get it in terms of u and v, probably. Yeah, because here, notice here we were able to solve for x and y in terms of u and v. So now you could just take x squared plus y squared. But it would be more difficult, right? So this one was cleverly contrived so that it came out nicely. You could always do it, but in the end you might not get something that was easy to integrate. So maybe the change of variables you chose was a bad one or something like that. Yeah. Okay, so now we have this thing, and we can do it. So this is the integral from v equals negative 1 to v equals 1. Let's see. Of the integral of 1/2 uv du. Can you figure out what that is? It's like 1/4 u squared v from u equals -1 to u equals 1 dv. Okay, let's do this. Integral from v equals -1 to v equals 1 of 1/4, let's just say v over 4 times u squared when u is 1 is 1 minus u squared when u is -1 is 1. So it's 0. So this 1 minus 1 is 0, and so the whole thing is 0. Okay, let's do one. The last one will be a little bit different. So I'll write it down, and then I'll tell you why we're doing this one. So suppose you want to take the double integral over r of xy squared dA over the following region. I'll draw it over here so that we have a little bit more space. So we have the line, the curve. We have the curve x times y equals 1, and we have the other curve x times y equals 4. And then we have the curve x times y squared equals 1, and the curve x times y squared equals 4. So those are our curves. And R is the region in the first quadrant bounded by those 4 curves. So there's our region R. Now the other one, you could have done it by hand, setting it up in the ways that we've done before. This one will be a huge mess, because you'd have to probably have break it into 3 regions. These 1, 2, 3, they would each be a mess. Life would be bad. So let's see if we can do this with a change of variables. So let's change variables. So u is something and v is something. Okay. So there are a couple reasons why we're doing this new example. The first is that you really can't do it any other way. And the second will be that we also can't really solve for x and y in terms of u and v in this example. So let's set this up. It would be really nice if our u and v could just be these limits of integration curves. So let's let u equals xy, and let's let v equal xy squared. So then our region of integration is u going from 1 to 4 and v going from 1 to 4. So our region of integration in the uv plane, this was the xy plane, is u goes from 1 to 4 and v goes from 1 to 4. So it looks like this box. So our transformation t actually takes this box in the uv plane and sort of curves it. You can see how this is let's see. This was supposed to, yeah, okay. Okay, so these are the 2 yellow curves, and these are the 2 white curves. And it just took this picture and stretched it, our transformation t. Okay, there's our region of integration. So let's set up our integral. So the double integral over r of xy squared dA is the integral from v equals 1 to v equals 4 of the integral from u equals 1 to u equals 4 of this function. Actually, can we write that in terms of u and v? Yeah, you can do it. V, yeah, exactly. Okay. I'm reading your lips, but it's going to work out, okay? Times the Jacobian expansion factor times du dv. So all we have to do here is find the Jacobian expansion factor. Then our life will be awesome. So let's do it. So we want dxy over duv. So all we have to do is solve for x as a function of u and v, and solve for y as a function of u and v, and then we'll be good. Who would like to do it? Yeah, it doesn't look like fun, right? So let's not do it. Here's the idea. So we have this transformation that takes us from the UV plane to the XY plane. That's our transformation T. And we're trying to find the determinant of the matrix DT. But there's also a matrix that goes the other way. So T inverse goes this way. This is an invertible transformation. So if you found the determinant of the derivative matrix associated to T, and the determinant of the one for T inverse, these numbers would be reciprocals. The determinant numbers would be reciprocals. Another way of thinking about that is if T stretches you by some factor, T inverse compresses you by like 1 over that factor. So what we need to do is just take duv over dxy inverse. Here this inverse means 1 over it, since this is a number. So let's do that. So we want the determinant of the partial of u with respect to x, the partial of u with respect to y, the partial of v with respect to x, and the partial of v with respect to y. And once we get that determinant, we'll just take 1 over it. So let's do it. So that's the determinant of, okay, partial of u with respect to x. Can you do it? Y. Yeah. And the partial of u with respect to y is x. And the partial of v with respect to x is y squared. And the partial of v with respect to y is 2xy. And if we do this, we'll get that this is xy squared. And so when we take 1 over that, we get 1 over xy squared. And I remove the absolute value signs because we're in the first quadrant where everything is positive. Question?
Just to clarify, when we say it's an inverse transformation,
Yep.
we can just do 1 over the same way we would like an inverse of the scalar?
So I was using inverse in 2 different ways in this sentence. So the matrix transformation has an inverse, meaning like suppose my transformation was to smush everything. Then the inverse of the transformation called smushing everything is to stretch everything. So that's one way of using the word inverse. And then another way of using the word inverse is just like 1 over. The inverse of 5 is 1/5. But then the thing is that the determinant of a matrix inverse is the inverse of the matrix determinant. One of them is numbers and one of them is matrix transformations. Yeah?
Always assume transformation or is that something we have to figure out first?
You can, if you do a change of variables, the transformation should be invertible.
If you go from R, if you go from the different dimensions, so if you say you go from R to R3,
Yeah.
or vice versa, then would you still be able to apply this? 'Cause
If you change your dimensions like from R2 to R3 or R3 to R2, you can't do it. You just don't have enough variables, actually, right? Because you start with a 2-dimensional thing. If you put it into 3 space, you're only going to get a 2-dimensional thing out. You're not going to get all 3 dimensions. So a way to make a non-invertible transformation, for example, would be to say u equals xy, v equals 10. And that wouldn't be invertible. Yeah. OK, so this turns out to be 1 over xy squared, which is 1 over v. So just to have a triumphant conclusion, v times 1 over v is 1. So we get the integral from 1 to 4 of the integral of 1 to 4 of 1 du dv, which is just the area of this box. The area of this box is 9, exactly. So it just comes out to 9. So this amazing, complicated thing that we could never have done, we'd have to do it in 3 pieces and they'd all be hard, came out to just something we could do in our head, which was 9. Pretty neat, huh? OK, thanks, everyone.